Hi, my name is Sean Breckling, and I'm an applied mathematician or a numerical analyst. Numerical analysts are interested in computing and approximating things. For example, a circle contains more information than you can store on any computer. So someone like me might come along and say, you could approximate that with a polygon. If you want higher accuracy, just pick more sides. We bring, essentially, that to solving complicated problems in math, physics, economics, anywhere. I work in fluids, and most fluid models are actually based on something called the Navier-Stokes model. And the Navier-Stokes model is actually a very difficult set of equations to work with, because on paper, you can't get an answer very easily at all. They're almost insolvable. So you need a computational touch. And even that is difficult, because if you look here, you see this nice smooth flow? That's called laminar flow. Laminar flow is easy to approximate, but it's this messy bit in the middle. That's called turbulence. And turbulence is extremely difficult to work with, because for practical problems, like a plane in the sky or a boat in the water, the resolution that you need to compute to get a good, accurate result is beyond even high-performance computing centers like my previous. It's just impractical. So someone like me, someone who wants to approximate, might suggest something called a large eddy simulation. In particular, the one I'm investigating called the Navier-Stokes alpha model. And what this model does is as you look at the physical settings of a problem, it computes an answer while trying to smooth out this irregularity, while at the same time maintaining these nice big features where all the energy of the problem is stored. And the result of that, you can see here, is if you have all these features smoothed out, you could see that the largest features are in fact maintained. Now, the net result of that is I have a direct comparison here between two numerical schemes using essentially the same discretization setup. And one thing that my model here does very well is it preserves physical properties. Like in the discrete sense, in this computational setting, my model can conserve mass, can conserve energy, can conserve more complicated things called helicity and entropy. It can conserve all these properties, which the net result of that is, if you look, when I try to infer something like lift, I get a massive amount of accuracy for a negligible amount of extra cost, which is incredibly important, because this kind of lift discrepancy in a professional setting can blow the wing off of an aircraft, and I would not like that. My research shows up in software packages used by engineers, used by climate scientists, used in the medical research for heart and blood, and I'm interested in more efficient and more accurate models all the time. Thank you very much.